Now, going back to our original pathway where we had the production of HMG-CoA, I noted that HMG-CoA was a branch point between synthesis of ketone bodies and the production of cholesterol. So now I want to follow the pathway that leads to cholesterol. The step that converts HMG-CoA to mevalonate is probably the most important step in the synthesis of cholesterol. And it's important because the enzyme HMG-CoA reductase is a regulated enzyme in cholesterol synthesis. In fact, it's the only regulated enzyme in cholesterol synthesis. This enzyme is interestingly inhibited by the byproduct of its pathway, that is cholesterol. So cholesterol can feed back, and when cholesterol accumulation gets too high, it will turn off this enzyme, and it will turn off the pathway that leads to the synthesis of cholesterol. Now, that's important because the synthesis of cholesterol requires a lot of energy. It requires many steps. And if the body is making too much cholesterol and doesn't need it, there's no reason to waste energy in making additional cholesterol. So this enzyme plays a critical role. Well, we all know, of course, that our cholesterol isn't always maintained at the levels it needs to be, and there are some complicated reasons why that's the case. But this enzyme is also useful from a medical perspective because this enzyme is the target for cholesterol-lowering drugs. So we've probably all heard of what are called statins, S-T-A-T-I-N-S, and these are molecules that resemble HMG-CoA. So they're competitive inhibitors of this enzyme. And as a result, when this enzyme is inhibited, again, the entire cholesterol pathway itself is inhibited. Well, this mevalonate is converted into the 5-carbon precursors called isoprenoids that are used to assemble the cholesterol molecule. These 5-carbon molecules are made by decarboxylating mevalonate. You may remember that mevalonate had 6 carbons in it, but the isoprenoid molecules used to assemble to make cholesterol only have 5 carbons. And these are the molecules you see on the top of the screen: isopentenyl pyrophosphate, called IPP, and dimethyl allyl pyrophosphate, called DMAPP. These two molecules are what we describe as the building blocks of cholesterol that go together to make larger molecules, as we shall see. Now, in this first step of the process, we see IPP and DMAPP that are joined together to make a 10-carbon molecule. So each IPP and DMAPP has 5 carbons. The 10-carbon molecule that's produced is called geranyl PP, or geranyl pyrophosphate. Addition of another IPP causes production of a 15-carbon molecule called farnesyl pyrophosphate. And joining 2 of those farnesyl pyrophosphates together creates a 30-carbon molecule called squalene. Squalene is the last of what we describe as the linear intermediates in the synthesis of cholesterol. And squalene's bonds can be rotated around and around and around to create a circular structure that looks like this. Now, there's a couple of steps involved in that I won't go through. But the first cyclic intermediate is the first thing that starts to look like cholesterol in the biosynthetic pathway, and this molecule is known as lanosterol. So lanosterol is the first molecule that's produced that looks like cholesterol. But before we talk about that, I want to remind you that everything that you've seen on the screen here was produced as a result of carbons that all came from acetyl-CoA. So very large, complicated molecules have very, very simple roots. This is the root of what we call anabolism.